So, welcome to our next section, which is about the evaluation measures for regression. So, in this fairly simple section, we'll cover the definitions of a couple of different performance metrics for regression. So, the mean squared error and the mean or median absolute error, and both of these are basically simply variants of the L1 and the 2 loss, which we have already studied in depth here in this lecture. We'll also discuss definitions of the more classical R-squared, which is a common measure for evaluating the linear model, usually in sample, and then I'm discussing that this can also be generalized to test sets and other models and other situations. And we'll also discuss the Spearman's rho as a performance metric to measure trends and relative ranks in our predictions, if we're interested in that instead of the concrete values. Okay, let's start with the MSE. So, as I've said before, MSE is nothing more than measuring for each element in our test set, where it's just kind of generalizing the L2 loss to a performance metric for an M size test set. And we're using again our compact notation here of putting all true labels, which are M elements for a given arbitrary test set in one vector, and then all elements of predictions on that test set, either in this vector or in general matrix capital F. And the definition of the MSE is, as I've said before, now nothing else than measuring for each point in the test set the squared difference between the prediction and the true label, and then averaging all of these guys across the whole test set. Because this is nothing more than the well-known L2 loss in disguise, we already know that it's heavily influenced by large residuals as they enter quadratically. You can also see here a visualization of the L2 loss, which I hope is not necessary anymore because you already know that. You can see here for a given data point, if you predict that with that linear model, the measured residual here, so the difference between f hat and y, and then we would square that to produce our loss value. Or you can also visualize that in this usual residual loss plot curve here. And there are different variants of the MSE, so we could also use the SSE instead, where we wouldn't average, but simply sum up all of these squared residuals. Or if we, and we usually want to bring back that MSE value here, which is still a squared entity, back to the original scale of our Y labels, and we take the square root at the end, and then we would have the RMSE. Now there's also the mean absolute error. This is nothing more than generalizing our L1 loss function to a performance metric rho. We would call that the mean absolute error if we would average over these L1 values here. And we know that this would be quite robust and would be less influenced by large residuals than the MSE, or we could even take the median absolute error, so exchanging this average here against the median, and then this would even be more robust. You can see the visualizations here of the L1 loss. I'll keep that very brief now, as we've discussed this before at times and times again. This measure here you might have not seen before, so that's the MAPE, the mean absolute percentage error. So this again computes the absolute value of the residual, but then sets this into relation to the true label y by dividing by y. So this simply computes the relative error of our prediction. And of course, this implies that smaller absolute values of y now influence the error measurement more strongly. So if you have a very small value for y, but you are quite far off in terms of percentage points, and not necessarily an absolute value, but in percentage, this will still influence your MAPE measurement quite strongly. Here this is visualized. It's not so easy to actually visualize that. You can see here the loss plot, and in terms of the residuals and how that actually enters the computation. So there are more variants of that simple MAPE measure. There's also the mean absolute scaled error, and there's also the symmetric mean absolute percentage error. I mainly wanted to name drop them here. I'm not even giving the definitions by formula. There's also the well-known R-squared measure. This is quite well known as a classical measure in classical statistics for evaluating linear models, and usually this is done on training data. Before we can discuss whether this also makes sense in machine learning, let's take a look at the formula and take that apart and see if we can understand its structure. So here is the formula of the R-squared. We can take a look at the numerator first here. So the numerator is nothing more than the SSE of the prediction of our given model. So for example, our linear model. Now the denominator is again an SSE, but it's the SSE of a constant model that we would have also in this case fitted on the training data. So let's kind of make our scenario precise here, our context. So let's stick with the linear model. We'll use that and evaluate it with the R-squared, and we'll also assume that we have simply using a training set evaluation strategies. The complete test set, so to speak, would simply be our training data. So in that case, we would measure the SSE of our predictions of the linear model on the training data set here, and we would compare that with the SSE of a constant model that we also have fit on the training data. So what that actually tells us now is how much the SSE is reduced if we go from a simple intercept model to a more complex linear model. So for example, if the SSE of a simple constant model on the training data is cut in half by going to a linear model. So for example, we would have an SSE of 10 with the constant model, but a linear model would produce an SSE of 5. This here would be 0.5. And in total, if we do 1 minus to complete the R-squared computation, we would have an R-squared of 0.5. So an R-squared of 0.5 means SSE is reduced by a factor of 2 by going from the simple intercept model to the more complex linear model. So in a certain sense, we are figuring out whether it's worthwhile to use a more complex linear model. It can outperform the intercept model in a reasonable manner. If, for example, the R-squared would be 0.9, we would know this second guy here must be 0.1, which means by going from this guy to this guy, a reduction of a factor of 10 has happened. So R-squared of 0.9 means the SSE is reduced by a factor of 10 from the intercept model, by going from the intercept model to the linear model. So we can now easily see that this measurement here is always in the range from 0 to 1. First of all, it can never be more than 1 because we are subtracting a positive term here, so a non-negative term. So both SSEs here have to be non-negative. So the resulting division must produce something that's also non-negative. So this is here always 1 or less than 1. It will also be 0 or more than 0 because for the R-squared to become negative, this second guy here would have to be larger than 1, which could only happen if the SSE of our linear model would be strictly larger than the intercept, but that can't ever happen on a training data set, right? Because we are optimizing the linear model for minimal SSE, and the model class of the linear model includes the constant intercept model. So it can only be as good as the intercept model or hopefully better. We can easily, before we generalize that, let's take one look at a interesting counterexample where R-squared or better R-squared not necessarily does imply a better fit. So here we are using a really, really simple data situation where we are sampling our observations from a simple straight line with some Gaussian noise on top of that. And I'm now restricting the range of my x values from 0 to 0.5. And I'm sampling from this straight line. And I'm even fitting now with the straight line with the linear model, and I'm measuring the R-squared and I'm measuring the MSE. So the MSE for that linear model is simply 0.02 and the R-squared is 0.75. Now in the next simulation, I'm simply going to extend the range of my x to go from 0 to completely 1. You can see that the fit of my model really visually hasn't improved at all. It's of the same quality as before. I kind of have the same a variation of my data points going on here for each position in X. And you can also see that the MSE point-wise is exactly the same. It's still 0.2, which is pretty much nearly exactly the amount of standard deviation that my Gaussian error here produces that I'm adding to the linear model. So that's the MSE measurement captures that actually quite well. But the R-squared is now actually increased. And the reason for that is because if I compare now on the left-hand side, my constant model, which would probably look like that, to my linear model, and I would do the same here, so maybe here, you can see that on the right-hand side, the constant model, just by increasing the range, is worse off in terms of SSE than on the left-hand side, and that's the reason why I'm seeing a better R-squared value here. So be a little bit careful here. On the other hand, what's actually quite nice about the R-squared is that this is completely invariant under any linear scalings of y, while the MSE is not. And in general, it's a nice measure of comparison, which I want to discuss a little bit here on this slide. So there are different ways of calling various variants of the R-squared. So I've chosen to call this, the result of this discussion here now, the generalized R-squared for machine learning. This terminology is maybe not super common in every paper or book, but be it as it may. The point that I want to drive home here is that this general principle behind R-squared can also be quite useful for ML. So first of all, nobody is restricting us to apply this general idea of comparing a simple model to a more complex model. Nobody is restricting us to use training data here. So we can do the same thing also on test data, which we would generally do in ML. And we can even use different loss functions or performance metrics to compare. And we can even compare different model classes. So we could, for example, compare an arbitrary machine learning model to a constant on test data with the L2 loss function or with the MSE or SSE, that wouldn't matter in that case. And then have an R-squared on test data for an arbitrary nonlinear regression model. Or we could even compare what happens when we go from a tree to a forest, or from a model with fewer features. So constant model is also a model with very few features, 0 features, to a model with more features. Or we could even use different performance metrics if we could do that for the L1 loss instead of for the L2 to even generalize the idea further. Of course, we now have to be a little bit careful. So the measure can now become negative. So if we have very difficult data situations at our hand where modeling is, let's say, nearly impossible, nothing really works out for us, we could actually see a negative R-squared on test data that very often leads to confusion for users because they sometimes think there's a bug in software. But that can really happen if we fit both our models, as we should do on the training data set. So we fit our constant model on the training data set, and we fit our more complex machine learning regression model on the training data set, then have them predict on the test set, and our regression model actually fares worse in terms of prediction than the constant model itself. Of course, in that situation, our regression model is basically worthless, right? It predicts really badly, but computationally or numerically, we could really then observe a negative value here, if that happens. Of course, like as I've said, we would kind of immediately throw our regression model away in that case, because it would perform even worse than a super simple constant model. Last slide. So if we don't care that much about the exact prediction values of our regression model, but we care about their relative ranks and whether the ranks in our predictions coincide and correlate with the ranks of our true labels. So we would capture kind of the trend correctly in our predictions, but not necessarily the exact values. We might use Spearman's rho here. So you hopefully also know this as the ranking correlation instead of the linear Pearson correlation. So this metric here simply now measures Spearman's ranking correlation between the vector of true labels and the vector of predictions through that very well-known formula here. So that's just the formula of the correlation applied to the rank transformation of y and y hat. And this is quite robust against outliers. A value of 1 would indicate we would have a perfect isotonic, so monotonically increasing relationship between y and y hat. Value of -1 would mean that we would have captured exactly the opposite trend in y hat than y. I guess that's nothing we would usually like to have, but this is what -1 would imply. And this measure is also invariant under monotone transformations of our y hat.